Hello and welcome to this MCMA webinar, Motor Standards Update. My name is Joanna and I am the Manager of Marketing and Membership for the MCMA, and I'll be serving as your moderator today. Attendees that have joined this webinar have joined in listen-only mode, which means that you are muted. If you do have a question during this webinar, please submit them in the questions panel of your webinar screen, and we will answer all questions via email after this webinar has concluded. This webinar will be recorded and a link will be sent to you within the next 24 hours. And now I'd like to thank our sponsor, Kingstar. Kingstar is a complete motion control and machine vision platform that creates PC-based machine controllers with premium precision and performance. Built on the EtherCAT standard and enhanced by the power of a real-time operating system for 64-bit Windows, you can use a single industrial PC to deliver software-only motion control and machine vision automation quickly and cost-effectively. I'd also like to introduce our presenter of today's webinar, Kristen Lowatsky. Kristen is a contributing editor for Motion Control Online and has written about motion control and automation for more than 7 years. As a technical writer, she covers a variety of subjects ranging from memory and microelectronics to nanotechnology to lasers and photonics. Kristen previously worked as an engineer on NASA's Chandra X-ray telescope before switching to writing about technology. Kristen holds a Bachelor of Science degree in physics and a master's in optics and photonics from the University of Central Florida. And now I'd like to hand it over to Kristen to get us started.
Thanks, Joanna, and thanks everybody for being here. So we've got June 1st coming up, which is always what I consider sort of the first day of summer, so yay on that, even though I realize it's not from a meteorological standpoint. But the other key thing that's going on is a very important piece of regulation goes into full effect, which is known as the Integral Horsepower Amended Rule, Amended Motor Rule. Say that one 5 times twice. Anyway, it comes into place, and if you haven't heard about it already and kind of done your advanced planning, you're going to get caught flat-footed because it's going to make some changes. The reason we're talking about it now, the rule actually applies to induction motors, continuous duty as opposed to motion control kind of thing, but it still has a number of applications, or there are things that you need to know about it if you're swimming in the motion control world. So first I'm going to be talking about the details of the regulation, kind of how all of that came together historically, some of the specifics of the Integral Horsepower Rule, also of something else called the Small Motor Rule, and kind of talk about why this is meaningful from a motion control standpoint, opportunities that might be opening up as a result of it, and so on. By the way, sort of an amusing fact, when all this first started, the Small Motor Rule was incorrectly referred to as the Fractional Horsepower Rule. Be careful that you don't misspeak it to that to anybody who's working on these committees, because they will correct you. So let's get to the motivations at first. There was a study, and this is actually a study from 2006 that the U.S. Department of Energy did on energy usage and so on. I went looking for a more current one, but I guess that's the last time they went through. But the numbers are pretty staggering. Motor-driven equipment consumes 1.4 billion kilowatt hours of electricity every year in the U.S. 1431 billion. That is a lot of energy. It's 38.4% of total U.S. electrical energy use. So motors are just gobbling it up out there. The industrial sector in particular consumes quite a lot, 632 billion kilowatts per year, or kilowatt hours per year in the industrial sectors, and about 62.5% of that just goes to motor-driven equipment. That's 44% of all motor-driven system energy So, when it started looking at ways to stop using so much energy, motors were a pretty obvious place to look. You're looking at 17% of the U.S. total electrical energy use. So if we could get more efficient in any small part on this, it would make a big difference. Motor regulation, there are the obvious motivations. Energy independence in this day and age is a big buzz, talking about trying to reduce greenhouse gas emissions, but there's also the whole energy cost. We've been in kind of a cycle where energy hasn't been as expensive. Last year, oil prices have dropped, but for a while there, it was sky high, and that was all coming off of the recession. You had companies really focusing on lean operations, and the idea of trying to swap out to get more efficiency started becoming a little more appealing. Efficiency, you're going to define that as continuous operation. Again, that's where it applies to AC induction motors. The legislation that we're going to be talking about, or the regulations that we're going to be talking about, primarily is going after continuous duty cycle AC induction motors that are used in compressors, fans, and pumps. And remember those scary numbers we were looking at. A lot of that is pumps that are just running all the time, or running when they're not supposed to be, or running and doing the job they're supposed to do. But if you get even a few percent increase in efficiency, you're going to get some savings in there. Now, the key thing here that makes this interesting to me is it doesn't apply to stop-start motion. It doesn't apply to intermittent. It's not really something that's going to, hit the motion control arena strictly, but it does have meaning for the area. Obviously, any factory, any facility you work in the industrial area, you've got it in HVAC, but if you're doing machines, on the production floor, you've got fans in your cabinets, you're working pumps for your water-cooled motors, you've got motors and fans, you've got compressors and pumps if you're building, filling and bottling machines and that sort of thing. You've probably got fixed-speed pumps going in those. CNC machines, you've got to have something to spray water or lubricant. You've got to have something to suck away the chips. They're out there, and it's not that the industry can afford to ignore it. The other thing I find interesting here, though, is that because of the things that you have to do in order to make the AC induction motors more efficient, it's actually opening up opportunities for permanent magnet DC motors potentially to step in. And that's where, servo motors, you slap on a feedback loop and yay, you're doing servo town. But you can also use that same motor technology elsewhere, open loop. So that's, and some of the stuff I'm going to be talking about later is kind of where I look at this as an opportunity for another market, an opportunity to get a foothold and eat the AC induction motor lunch. Not that I'm biased. So let's run through the history really quick on this whole thing. I believe there was actually some seminal legislation back in 1975, but the key where the motor regulation really started was 1992 with the passing of the U.S. Energy Policy Act. And that spawned the Electric Horsepower Rule. That was effective October 1997, and it covered general purpose polyphase AC induction motors, 1 to 200 horsepower, according to NEMA energy efficient levels. And the kind of the key thing, and there are places online, in fact, I've got a list of references and links. So if anybody is interested, in the last slide, I'll be showing my email address. Feel free to email me, and I'd be happy to send you the list of places that you can plumb to get all of the details. But basically, the the key thing is, it made a start, but there were so many exceptions that there were as many motors not covered as were covered. So then the next update happened in 2007 with the Energy Independence and Security Act. Part of this legislation, too, that came in is they were mandated to, the Department of Energy was mandated to do regular updates. So throughout, I think it's every 5 years, they have to run through and review and revise and see when it's time to upgrade. So that's part of what ISO was about. It was effective December 2010, and it pushed everything farther. It didn't do it completely, but it did raise kind of the basic, the 100 to, or the 1 to 200 horsepower motors, push them from NEMA energy efficiency to premium efficiency, or energy efficient to premium efficient. It also added 201 to 500 horsepower motors to energy efficient and pulled in some formerly exempt motors to energy efficient. So it did increase the stakes in all of this, but mostly you're looking at general purpose stuff, nothing modified, nothing application specific, like fire pump motors for a long time weren't touched because they were considered low duty cycle. Motors for arbor saws weren't on the list. And people started kind of getting old cute with it because it said, okay, if you do customized or special purpose motors, then you can be exempt. So what do? You put a different flange on it. You do something a little different with your mount that makes it a little custom. Suddenly it's not quite stock, and guess what? You don't have to do anything about raising the efficiency. So then it became time to take a look at those loopholes. And as I was saying, the DOE is supposed to keep reviewing the standards. Now, an industry group pulled together called the Motor Coalition, because one of the things that they figured was coming was going to be another energy jump, maybe to the next level. And that takes a lot of doing when you're a motor manufacturer. It's not just new designs, it's new tooling, new production lines. It's a whole different area, and suddenly all of your customers out there, have to rethink their products. They have to rethink what they're doing. It's, a supply and sourcing issue. So they developed this coalition that volunteered to work with the DOE, said, hey, you know what, instead of just jumping up to the next level of efficiency, how about if we cut off a bunch of those loopholes? Because right now there are more motors that are exempt than not. So let's get in there and start smacking things around. So that was the next level. And yes, here we are today at the Integral Horsepower Amended Motor Rule. That was finalized 2 years ago, May 2014, and it's effective in about a week. In this particular case, almost all motors, 1 to 500 horsepower AC induction motors, have to meet NEMA premium efficient levels. They believe that that's going to save over the period of time, 2016 to 2045, that is going to save a ton of energy. It's going to pull 395 million metric tons of carbon out of the atmosphere that otherwise would be contributing to global warming. From the standpoint of owners, it's going to do a net savings in cost of ownership. And if you haven't heard the ongoing discussion about cost of ownership and power savings, you've been living under a rock lately, because that's really been a big dialogue going on in terms of ways to find efficiencies in any kind of manufacturing operations, editing, auditing, and so on. If you can put in motors even in just your facilities and a few key places in manufacturing that are going to buy you some efficiencies, that's going to offset the initial outlay. And some of the key motors that got included, the second batch of 1 to 2 horsepower motors, they got pulled in under ISA as energy efficient. They now have to be premium efficient. Previously, energy efficient 200 to 500 horsepower motors are now supposed to be up at premium efficient. Things like motors with moisture resistant and sealed or encapsulated windings, they have to go. 56 frame and closed motors, I didn't put on the full list here because it goes on forever. But 56 frame and closed motors, they used to be exempt, now they're premium efficient. As I mentioned, the fire pump motors are still covered. And the key thing here is, remember we were talking earlier about people trying to dodge the regulation by doing a little bit of cute customization and stuff. That doesn't work anymore. Now, even if you've got non-standard plates and flanges, you've got unusual base or mounting feet, special shaft, even things like vertical or hollow shaft motors, a whole bunch of stuff that you would have thought would have been exempt in the previous rules. That's not going on anymore. Your arbor saw motors are now in there, and they've managed to bring a whole bunch of stuff in. Gear motors is another one. A whole bunch of stuff in under the regulation. Now there are still motors not covered. A whole variety, like 2-digit frames and open drip motors, all of that. But the key thing for what we're doing here is look at what else isn't covered. DC motors aren't covered. Intermittent duty motors aren't covered. Multi-speed motors aren't covered. Synchronous AC motors aren't covered. Permanent magnet rotor AC motors aren't covered. And of course, neither are servos. And I'll say more about that later, because that doesn't necessarily mean that people are skating off and being irresponsible. It has more to do with the nature of the technology, but it still means that there's an opportunity there in terms of getting market share. So as far as some of the specifics on June 1, what the legislation means is if you are a motor vendor, you should have been transferring over all of your tooling and planning your operations carefully, because as of June 1, they are no longer allowed to manufacture non-compliant motors for sale in the United States. They can still sell elsewhere as long as it meets regulations in that other location. They can also sell anything they have in inventory. What they can't do is finish any motors that are partly through the process. They've got to have everything out of their production lines and have that shut down. It's key to keep in mind that the compliance rests with the manufacturer. If you're an end user, you don't have to worry about this as long as you tell them where you're located and make the buy. That doesn't fall on you. So it's incumbent on them to make sure that they are selling you a compliant product. But yes, there is more. So that horsepower rule, small motor rule I was talking about earlier, that came along in between ISA and the integral motor rule. Passed in 2010, became effective in March of last year. So that is, they're not held to a NEMA standard. They're actually numbers put together by the DOE. And they apply to 1/4 to 3 horsepower motors. And that's kind of where they got started with the names, you know, fractional because that's a fraction, integral because the other ones were whole numbers, but fractional doesn't apply because over time, developing the standard, they extended it out from just, you know, 1 and smaller to taking out to 3. There are a whole number of specifics, but in particular, it applies to single and 3-phase motors, 2, 4, 6 poles, and standard construction. And that's where we get to that same thing where you've got loopholes for people. They, you know, if you're application specific, no, that won't work. If it's an air over an enclosed motor, no, it doesn't count. Standard construction. But that said, you know, we've been through the process with the bigger motors, and you know, they close it down bit by bit. They tighten the loopholes, and as time goes by, more and more things get covered. So expect to see that whole process. Now, this isn't just happening in the United States. I mentioned earlier about the need to follow what's happening with your local legislation and so on, because it's very much global. And this plot shows you kind of how the different standards stack up. IEC has developed a list of standards that stack up against the NEMA standards. There are other standards in other areas of the world that do the same. Now, top to bottom, IEC, you know, NEMA, you know, AS, NCS, that's Australia, New Zealand, ABNT is Brazil, and down at the bottom, China is indeed China. But we also have a very nice map that gives you a better fix on all of it. So. Now let's take a closer look at what goes on with the loss mechanism. A lot of it is resistive losses from windings. Obviously, you've got windings in the rotors for an AC induction motor. You also have eddy currents in the rotor laminations. You get hysteresis. It adds up. About 25% of losses come from the rotor alone. So the question is, what do you do from a design perspective? More copper for start. Resistance goes as the inverse of the cross-sectional area of the wire. So if you use larger wiring, you're going to cut your resistive loss. That does bring up a couple of key points. The motor is going to get larger because you've got to use more copper. It also illustrates that it's going to be harder for the people having to deal with the small motor rule because they don't have these, you know, the acreage to deal with that you have in the larger motors. So it's kind of a challenging design process. And I like this, when I was talking with John about this, at one point he mentioned that. It's hard not to do it right when it's a big motor, and it's hard to do it right when it's a small one. Other techniques that you can use to increase efficiency, you can switch from aluminum rotors to copper. People have been getting good results with cast rotors. You can go to thinner laminations, and they get really thin. There's some work underway, specialty alloys for laminations, in particular doing amorphous rather than crystalline laminations. The problem is with some of those structures, they're so thin and they're so brittle, it's really, really hard to work with them. So it's not clear that that's ever going to be able to really translate from the laboratory into a production environment and something that's going to be rugged enough to go out on a factory floor and be there for years. So the net result you get these higher efficiency motors, yay, we're saving money, we're doing good for the environment, et cetera, et cetera. We're buying new motors. But you also wind up with motors that are larger. They're going to be heavier, depending where they're at. You may have to change your mounts. You may have to lower things or do something so that things will match up. But kind of the tricky part is going to be, we were talking earlier about using some of these motors inside machines. If you got a filling machine or whatever, and you don't have a lot of space, that's where you start running into trouble. In fact, one of the guys I spoke with about a year ago said that they really went round and round with the DOE on that issue when they were talking about making these standards, because suddenly people are going to have need for motors, and it's not necessarily conducive to retrofits. I mean, machines, and we'll see more about this later, but machines are out there running for 20, 30 years. And if you run out of the old style motors that you stocked up before the rule went into place, you're going to be a hurting unit unless you can get somebody to customize a motor for you, and that's not going to be a happy thing. So going beyond the whole issue of size, there are also just overall design points to watch. AC induction motors have slip because once it takes time for the windings in the rotor to get energized so that you can start some magnetic interaction happening. And when you make them more efficient, that slip drops. Now, normally you would say, yay, we're happy about that, we've got better operation, but it can actually complicate the design and the operation of your machine, because all of a sudden your speed's not the same. When your speed's not the same, your horsepower potentially changes, and you might wind up having to look for a motor with different torque characteristics and so on in order to let you do what you're trying to do. So it's not just complicated because of the size thing. It's potentially going to be challenging because the motor performance is not going to be the same, which is where permanent magnet motors may just be a good solution. Rotor losses. You don't have windings on the rotor in a permanent magnet motor. So that means right away all of those losses go out the door. Now, there are some trade-offs, and there are definitely arguments. I strive to remain quite even-handed anytime I'm writing, covering this area, but there were several people that I've spoken with over the past year on this topic who were frustrated by some of the comments against permanent magnet motors that have been made that they kind of viewed as not necessarily equal comparison. So the first argument is, look, they need drives. Drives cost more, they take space. Yeah, they do, but they've gotten cheaper, they've gotten smaller. It's really not as big of a differential as you would think, especially stacked up against the higher cost of the higher efficiency motors. But here's the big controversial thing. Drives reduce efficiency. Now, admittedly, they do. If you've got an induction motor and you slap a VFD on it, then you're going to lose efficiency, because induction motors like clean sine waves. They want that clean wall plug power. And unfortunately, drives don't produce sine waves that are clean. Better drives produce better sine waves, but that isn't always the case. And that's where I heard a fair amount of frustration, because when you're comparing efficiencies, you need to be careful that it's apples to apples. An induction motor has an efficiency. You put on a drive, that efficiency drops. So you've got the published efficiency of the motor, and then you subtract the efficiency hit from the drive. that's not what you do with a permanent magnet motor, because you can't run a permanent magnet motor without a drive. So any published efficiency you see for a permanent magnet motor always includes the drive loss. So if you're having somebody compare, you don't subtract that out. And several people, as I say, I spoke with were kind of aggrieved that sometimes the numbers get applied somewhat indiscriminately. You use bad drive, that can cut your efficiency. So just, I guess the comment I'm trying to make with this slide is pay attention if you're out there as an end user and considering between the two technologies, because you want to make sure that the numbers you're looking at accurately represent the situation. Now, all of that said, permanent magnet motors can really be great in a number of situations. In general, AC induction motors like running at high speed. That's where they're most efficient. And there are a lot of different sizes out there, kind of standard. But just let's look at an example, air handling fans. 1800 RPMs is a really common speed. That's your 8-pole motor. And the problem is that air handling fans tend to be most efficient between 500 and 900 RPM. So if you're putting an AC induction motor on it, you can direct drive the fan and just run your 8-pole motor more slowly. You can put a variable speed drive on it, and that's going to take it to 900 RPM, or you can put belts on it. You put belts on it, all of a sudden you've got a maintenance issue, you've got a point of failure, you've got additional cost. So, that is a way to do it, but you're not going to be able to escape the fact that if you're running a permanent magnet motor, not permanent magnet, an induction motor, at those speeds, that you're not getting the performance that you would like to get. And also, higher pole count motors cost more, so that's part of the problem too. Oh, the other thing, yes, I forgot. Cutting speed, it's going to magnify slip because it's suddenly a much larger percentage of your RPM. Variable speed drives are going to cut efficiency. We already had that discussion about it cuts efficiency on permanent magnet motors too, but that's already folded into the number that you're looking at, and your belts also cut efficiency. Direct drive permanent magnet motor, you can get right in there whether you're going fast or slow. You're getting full torque. You're going to get a high efficiency boost. I should have attributed this, but this came from a calculation by John Petro, who's a motor designer. The motors are going to be smaller. They're going to be lighter. You're not going to need those belts. As I said, you're going to have a drive. True, but it's already factored in. And because of the design of the motor, it's not going to have, it's not going to be as big size. So we've been talking about the IE, various and sundry IE ratings. Now, right now, as I mentioned, we're looking at IE2 and IE3. That's NEMA energy efficient and NEMA premium efficiency with parallels in the other standards. There is work going on out there, though, with IE4 and, quote, IE5, because IE5 hasn't really been developed, but people have done sort of theoretical modelings of what an efficiency curve that met that criterion would look like. And at the very top, the JP numbers, that's, again, calculations by John Petro, kind of to back up a discussion of this type. that we could go there eventually. There are a couple of companies out there already we'll talk about later that are actually fielding IE4 and IE5 motors, despite the fact that the legislation hasn't mandated them, but they're getting a call for them out in the field. One of those designs is to use focused flux. Your standard motor, and I was trying to get a picture of this, I had trouble. Standard motor is basically straight, right? It's rotor on the inside and stator on the outside, or vice versa. But you've got straight lines of flux. What these guys have done is built conical rotors so that it focuses the flux in 3D. So now you don't have a flux return path in the stator. That's going to lower your stator losses, and it starts boosting your efficiencies. You get performance comparable to that of a rare earth permanent magnet motor, but you can do it using ferrite. In fact, they've gotten to 95%. And the other key thing is, as with permanent magnet motors, but other types, you get constant torque over a wide speed range. Another approach is the synchronous reluctance motor, and that can get you very high efficiencies. You get rid of the rotor. You just have lamination. You need to have a drive. It's a little more complex, and it's going to cost a little more. But again, you can use ferrite magnets. You can get pretty high outputs. And then you've got, and the IE5 thing, by the way, I should have had quotes on that throughout, because that's kind of one of the things that's going on. It's not actually defined as a standard as yet, but it's out there for people who want it. I don't know what they're going to say if they ever go to IE6. They've already used premium and super premium and ultra premium, and I don't know if it's going to be titanium, platinum premium, or what. They're going to have to work on it. Maybe with the people who come up with names for cards. Anyway, permanent magnet motors. Again, you use the magnets, you got the rotor losses, you can get IE5-ish performance for motors up to 160 kilowatts. Now, one of the things that I came across in the process of working on this last year was a really interesting study from Sweden. And what they wound up doing was, it was part of a government program to see if they could see what the level of efficiency was being used, and then start encouraging companies to swap over and kind of see how the process went. They devoted some public funds. They added a small surcharge to the utility bills company-wide or countrywide. I think they funded it for a couple of million. So part of doing this process, they studied 4,100 motors, and this was 2010 to 2014. And they discovered that more than half of the motors out there had already exceeded their rated lifetime. On average, they had been there twice as long. They get out there, they get rolling, and they just keep ticking. 19% of the motors had VFDs, the rest were still running continuous speed. And one of the really kind of useful things going on right now in terms of motor speed, or not motor speed, energy savings, is putting VFDs on things like fans and pumps and so on, so that instead of having the motor running flat out all the time and choking it down with a valve or something mechanical, you're having the motor itself do less, and it cuts energy usage hugely. And at this point, only 19% of the motors out there have them. They also measured 104 motors in depth. 2/3 of them showed that the average load factor was below 60%. So not properly sized, not taking advantage of new technology. So they sent people out, they worked with them, they got motors swapped out. The companies involved invested about $2.3 million in the swap over. Total savings were around 73.7 gigawatt hours over the expected lifetime of the equipment. And I assume that's a rated lifetime, not the amount of lifetime it's going to get when it's out there. That gave an average savings of 20 to 30%. And the study actually has full details. I think it was 62% improvements on compressors. Fans and pumps were a little lower than that. One of the interesting things about the study is they considered themselves surprised at how much assistance the people at the facilities needed in terms of sizing and installing the new motors. And the program as a whole went over its budget because they had to have so much technical expertise. So my takeaway with this is if you are selling permanent magnet motors, number one, there are a lot more opportunities out there than you might think. There are motors out there that really could stand replacing, that would give, with new technology, give good ROI. But the clients are going to need help. They're going to need help recognizing the issue, and they're going to need help designing it in and adapting to the new technology. And depending on what else they have in their facility and whether they're used to working with servo motors, there may still be people out there who aren't as comfortable with it as they are with AC induction. So, sum total to me, Integral Motor Amended Rule applies to manufacturers, not end users. If you're an end user, hopefully you have been thinking about this for a while and making your switch over, but if not, and if you go to buy a replacement motor after Monday, you might be in for a little surprise when it shows up, because it's not going to be quite like you expected. Higher efficiencies do save money, but they also result in larger, heavier motors. They also can introduce changes in the actual performance of the motor. And that's something that's really important to keep in mind when you're looking at these swap outs. Permanent magnets can make AC induction motors work better, but our beloved permanent magnet DC motors have a place to play here. So it's kind of something to look at as a market opportunity. And I think with that, boys and girls, I think we have come to the end of our time. Another thank you to the sponsor, Kingstar, for sponsoring the webcast, and thanks to everybody who's listening.
Yes, thank you, Kristen. And for those of you, we've gotten several questions that have come in for this webinar, and Kristen does follow up with all questions via email after this webinar has concluded. So if you do have one, there still is time to put that question in your questions panel of your webinar screen. And again, yes, I'd like to thank Kristen as well as our participants and as well as our sponsor, Kingstar. I'd also like to share with you about our next event that's coming up, which is our technical conference. For those of you who haven't heard, we're excited to announce that the MCMA will host its annual technical conference in the French Quarter of New Orleans in Louisiana. The dates are October 11th through the 13th. The conference will focus on practical training in areas of motion control technologies, electric motors, software, interface, network communication, and related technologies. We'll also offer a full tabletop exhibition with industry suppliers and networking events for all participants. It is a must-attend industry event. We hope that you will join us. Also, be sure to visit www.motioncontrolonline.org for more information about TechCon and other upcoming webinars. Thank you again, and have a great rest of your day.